Hello everybody, this is Dr. Thunder. Today, I would like to show you how to solve another US high school physics competition problem. So we have a vertical pole that has two massless strings here. Both have length L. These two strings attached to the pole with a distance L from the two attaching points. And then the other ends of the strings are attached to a mass M. The mass is rotated around the pole with an angular velocity omega. So we know that when the mass is rotated, there's some tension in the string. So assume the tension in the upper string is F1 and in the lower string is F2. So we want to know the ratio of F2 to F1 as a function of the angular velocity. So we want to find out that relation versus omega. So we know that when the angular velocity is very, very low, the lower string will be relaxed. That means F2 should be 0. So in the very beginning, when the mass is rotated very slowly, most likely we will not maintain this triangle. Possibly the position of the upper string will be like that, and then the ball will be like here. But now let's start with enough angular velocity so that we maintain this triangle with each side of L. So this angle will be 60 degrees, and then this also 60 degrees. So we start from there. So now we analyze the force on this mass. So we know this is a tension F1 from the upper string, and then tension F2 from the lower string. And then the mass also has a gravitational force mg. And then because it's rotated, so the centrifugal force is m omega squared r. So it's rotated like that. So let's look at the vertical direction first. So vertical F1, the component along the vertical direction of F1 is F1 cosine 60 degrees. The direction is up. And then the component of F2 along the vertical direction is F2 cosine 60 degrees because it points downward. So that equal to the gravity force mg. This can be simplified into, because cosine 60 degrees is half, so that becomes F1 minus F2 is 2 mg. And then for the horizontal direction, the F1 along the horizontal direction is F1 sine 60 degrees plus F2 sine 60 degrees. That equal to the centrifugal force m omega square r. Because sine 60 degrees is square root 3 over 2, so we have F1 plus F2 equal to m omega square r, and then divided by square root 3 over 2. But we know r, we know that here r is L, this is 60 degree. L, R sine 60 degree. So R is square root 3 over 2 L. So we plug R here. So we have m omega square L. Let me double check. R is here. So we plug here. Yes, it's m. So now from these two equations, we know that we add up these two equations. So we have 2f1. The f2 is eliminated. That equal to 2mg plus m omega square L. So f1 is mg plus half m omega square L. Then we we plug this here. So f2 is f1 minus 2mg. So it's minus mg plus half m omega square L. Now we want to find out the ratio of f2, f1. So f2 over f1 is, we plug this here, minus mg plus half m omega square L. f1 is here, mg plus half m omega L. So we can eliminate all m. And we move this term to the left. So we have half omega square L minus g over half omega square L plus g. So to make it looks better, so we multiply by 2. So omega square L minus 2g over omega square L plus 2g. This is a relation between the f1, f2 versus angular speed omega. So as we can see here, in the very beginning, when omega is small, the upturn is negative. But we know that negative will not make any sense here. So, when omega is below some value, f2 over f1 is 0. And then when omega is omega square L minus 2g is over 0, then this term begin to grow. But eventually, when omega is very large, g can be neglected. So f2 over f1 will approach 1 in the end. So the curve will look like this. Let's draw here. That's f2 over f1. This is angular speed omega. So in the beginning, it will be 0. But then at some moment it will begin to grow, and in the end it will approach 1. So thank you for viewing. If you like my video, please comment, like, and subscribe.